The morning of January 5, 1943, USS Helena, a Brooklyn-class light cruiser, cuts through dark water southwest of Guadalcanal. The sky above the Solomon Islands holds that deceptive pre-dawn stillness that every sailor in the Pacific has learned to distrust. Lieutenant William "Red" Cochrane commands the aft 5-inch battery. At 0630 hours, radar operators detect 4 contacts inbound at bearing 270, range 12 miles, altitude 8,000 feet, Japanese Aichi D3A dive bombers. Allied reporting name, VAL. The attack develops fast. One VAL peels off, diving toward the New Zealand cruiser Achilles. A bomb detonates amidships, damaging her superstructure. The remaining 3 bombers execute their runs and immediately break off, climbing back toward their base at Munda. Standard doctrine: hit hard, get out fast, stay below the American fighter cap altitude. Cochrane's gun crews track the departing aircraft. Range: 6,000 yards. Moving target: high deflection angle. Every instinct and every hour of training says this shot is nearly impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 shells leave Cochrane's 5-inch guns in rapid succession. They arc upward at nearly 3,000 feet per second, their trajectories invisible against the breaking dawn. No tracer rounds. Nothing to mark where the shells are going. The gunners track the bombers through their optical sights, waiting for something, anything, to confirm their aim. Then one of the VALs simply disintegrates. Not from a direct hit. The aircraft doesn't explode in a single catastrophic flash the way it would if a 54-pound shell had struck its fuselage. Instead, it comes apart structurally, pieces spinning away as if some invisible force has reached into the sky and crushed it. The VAL drops toward the ocean, trailing smoke and debris. No parachute deploys. What Cochrane's crews had just witnessed was something the Japanese pilot never saw coming. At least one of Helena's shells had detonated roughly 70 feet from the aircraft. The explosion created a spherical burst of shrapnel fragments traveling at thousands of feet per second. Dozens of these fragments, some no larger than a man's thumb, punctured the VAL's wings, engine, and cockpit. The pilot was probably dead before his aircraft began its final dive. The remarkable part wasn't that Helena's gunners had shot down an enemy bomber. Cruiser batteries had been doing that throughout the Guadalcanal campaign with varying degrees of success. The remarkable part was the mathematics of what had just happened. 3 shells fired, 1 aircraft destroyed, no direct impact required. By the standards of 1942, this was impossible. To understand why, you need to know what American anti-aircraft gunners had been dealing with for the previous 13 months of war. The numbers were brutal, and they'd been getting worse. In 1942, American naval vessels in the Pacific fired an average of 654 5-inch shells for every enemy aircraft they successfully destroyed. 654 rounds. Most cruisers and destroyers carried between 300 and 500 rounds of 5-inch ammunition total. That meant, statistically, you could fire your entire magazine at an incoming bomber formation, and maybe, if conditions were perfect and your gun crews exceptional, down 1 aircraft. The problem wasn't the guns. The 5-inch 38 caliber dual-purpose weapon that equipped virtually every American destroyer, cruiser, and battleship was arguably the finest naval artillery piece ever manufactured. Rate of fire: 15 to 22 rounds per minute depending on crew training. Muzzle velocity: 2,800 feet per second. Maximum effective range against surface targets: 18,000 yards. Maximum effective ceiling against air targets: 37,000 feet. The guns worked brilliantly. What didn't work was hitting anything with them. Anti-aircraft fire in 1942 operated on a principle called barrage shooting. Gunners would set their shell fuzes to detonate at predetermined altitudes, creating a curtain of explosions that enemy aircraft would theoretically have to fly through. The word theoretically carried enormous weight in that equation. The fuse setting process itself was complex and time-sensitive. Each 5-inch shell carried a mechanical timer in its nose that could be adjusted before loading. Gun crews received range and altitude data from fire control computers, typically a Mark 37 director connected to radar systems. A mechanical fuse setter, integrated into the shell hoist on most American vessels, would automatically rotate the fuse ring to the proper setting as the round moved from the magazine to the gun. In theory, this created precise control over where the shell would explode. In practice, it created a cascade of failure points. The fire control computer had to accurately determine the target's altitude. Radar technology in early 1942 was primitive by later war standards. The SC-2 air search radar carried by most American destroyers could detect aircraft at reasonable ranges but provided crude altitude data. The radar operator had to estimate angle of elevation, then apply manual calculations to convert that angle into actual altitude. Errors of plus or minus 500 feet were common. At ranges beyond 10,000 yards, errors could exceed 1,000 feet. Once the computer calculated altitude, it had to predict where the target would be when the shell arrived. This required knowing the aircraft's speed, heading, and whether it was climbing, diving, or turning. Combat aircraft rarely obliged by flying straight and level. A Val dive bomber approaching at 240 miles per hour could cover 600 feet in less than 2 seconds. If the fire control solution was even 1 second late, the shell would detonate 300 feet behind where the bomber used to be. Then there were the fuses themselves. Mechanical clock fuses weren't precision instruments. They were wind-up timers subjected to 20,000 times the force of gravity during shell launch. The acceleration from 0 to 2,800 feet per second occurred in approximately 0.02 seconds as the shell traveled through the gun barrel's rifling. That's 20,000 Gs compressing and stressing every spring, gear, and pivot point in the fuse mechanism. Manufacturing tolerances meant each fuse performed slightly differently. One might detonate exactly 28 seconds after firing. The next might go off at 27.8 seconds. The third might wait until 28.3. At a muzzle velocity of 2,800 feet per second, a half-second variance translated to 1,400 feet of error in where the shell exploded. And all of this assumed the target maintained constant altitude and heading. Admiral Arleigh Burke, commanding Destroyer Squadron 23 during the Guadalcanal campaign, later described anti-aircraft gunnery with time fuses as bringing down a plane at night by accident. He wasn't being dramatic. He was being statistically accurate. Navy after-action reports from late 1942 showed that barrage fire's primary value wasn't actually shooting down aircraft. It was psychological harassment. The sight of black smoke bursts filling the sky around them made Japanese pilots nervous, forced them to take evasive action, disrupted their bomb runs. But the actual probability of a time-fused shell detonating close enough to a maneuvering target to cause lethal damage remained below 2%. This created an ammunition logistics problem that threatened to collapse the entire American defensive posture in the Pacific. Consider the destroyer USS Fletcher, commissioned in June 1942 and immediately deployed to the Solomon Islands. Fletcher carried approximately 400 rounds of 5-inch ammunition. Her 5 main guns could fire a combined 100 rounds per minute at maximum rate. If Fletcher came under sustained air attack, and her gunners maintained even half that fire rate, they could expend their entire ammunition loadout in 8 minutes. Admiral Chester Nimitz, Commander-in-Chief Pacific Fleet, reviewed the ammunition consumption figures in late 1942 and recognized the mathematics weren't sustainable. American industry could build ships faster than Japanese shipyards. American training programs could produce sailors faster than Japan could replace losses. But if every engagement required burning through 500 rounds of 5-inch ammunition per kill, the logistics network couldn't keep pace. The supply ships hauling ammunition from Pearl Harbor to Noumea to Guadalcanal were becoming primary targets. Japanese submarines prowled the supply routes, specifically hunting the slow-moving cargo vessels that carried ordnance. Losing an ammunition ship meant dozens of cruisers and destroyers operating with reduced magazines, which meant reduced effectiveness, which fed back into even higher ammunition consumption rates. Someone had found a better solution. That solution had been sitting in a laboratory since August 1942. The Navy had tested it, confirmed it worked, and then faced the uncomfortable reality that building it at the scale required would demand retooling a significant fraction of American industrial capacity. The technology was called a proximity fuse. The Navy's code name for it was VT, standing for variable time, a deliberately misleading designation chosen to obscure what the device actually did. What it actually did was revolutionary, and it started with a problem that seemed unsolvable, putting a radio inside an artillery shell. End of opening section, continuing. The idea of a proximity fuse wasn't new in 1940. Military scientists had been proposing versions of it since the mid-1920s. The concept was elegant. Instead of trying to predict where to detonate the shell before firing, let the shell detect the target itself and detonate automatically at the optimal distance. But elegant concepts and functional hardware existed in entirely different universes. The British had attempted proximity fuse development starting in 1939, shortly after war broke out in Europe. Their initial designs used photoelectric cells that would detect changes in light intensity as the shell approached a target. The engineering team at the Woolwich Arsenal constructed working prototypes by mid-1940. These fuses functioned adequately in rockets, which experienced acceleration forces around 100 Gs and no rotational spin. Artillery shells were different. When fired from a 5-inch gun, the shell experiences acceleration of 20,000 Gs instantly. That's 20,000 times Earth's gravity crushing every component in the fuse. Then, as the shell travels through the gun barrel's rifling grooves, it begins spinning at 25,000 revolutions per minute. That's over 400 rotations per second, creating centrifugal forces that would tear apart conventional electronics. The British tried mounting photoelectric fuzes in artillery shells in autumn 1940. Every single test ended in failure. The photoelectric cells shattered. The mechanical linkages broke. The electrical connections separated. Even when components survived the launch, the rapid rotation disrupted the optical sensor's ability to detect targets. British scientists concluded that any fuse capable of surviving artillery launch conditions would need to be fundamentally different from anything they'd built before. They documented their findings and, in September 1940, shared them with American researchers as part of the Tizard mission. The Tizard mission was Britain's desperate gamble to keep fighting technology out of German hands if England fell. A delegation led by Sir Henry Tizard brought cavity magnetron designs that would enable high-powered radar, jet engine specifications, and stacks of research documents on projects the British had started but lacked resources to complete. Buried in those documents were 23 pages describing radio proximity fuse theory. The Americans read it and thought the British were insane. Building a working radio transmitter and receiver small enough to fit inside a shell nose, rugged enough to survive launch forces, and simple enough to manufacture by the millions, seemed impossible. Vacuum tubes, the only electronic amplification technology available in 1940, were delicate glass components. Dropping a household radio off a table could shatter its tubes. How could vacuum tubes possibly survive forces 20,000 times stronger? But the United States Navy needed a solution, and they needed it immediately. On August 12, 1940, Captain Gilbert Hoover, representing the Bureau of Ordnance, formally requested that the National Defense Research Committee begin development of rugged proximity fuses capable of withstanding anti-aircraft artillery forces. The NDRC assigned the project to Section T, a newly formed research group housed at the Carnegie Institution's Department of Terrestrial Magnetism in Washington. The section's director was Dr. Merle Tuve, a physicist who'd spent the previous decade developing radio equipment for atmospheric research. Tuve assembled a team that would eventually include over 800 scientists, engineers, and technicians working across multiple sites. Their deadline, though never formally stated, was implicit in every memo from the Navy. Enemy aircraft were sinking American ships faster than shipyards could build replacements. Whatever Section T developed needed to be in combat use before the Pacific Fleet lost control of the Solomon Islands. The technical challenges were staggering. Any functional proximity fuse needed to accomplish 7 things simultaneously. First, transmit a radio signal strong enough to bounce off an aircraft at distances up to 200 feet. Second, receive that reflected signal and detect changes in frequency caused by the shell's approach to the target. Third, amplify that signal sufficiently to trigger a detonation circuit. Fourth, power all of this electronics with a battery that could survive shell launch and function reliably in temperatures ranging from -50 to 100 degrees Fahrenheit. Fifth, ensure the fuse couldn't detonate prematurely during handling or storage, which meant multiple independent safety mechanisms. Sixth, fit all components into a space roughly the size of a pint milk bottle, the nose cavity of a 5-inch shell that also had to contain 7 pounds of high explosive. Seventh, accomplish all of this at a manufacturing cost low enough to build millions of units. And all of it had to work while spinning at 25,000 RPM and being subjected to forces that would flatten a human being into a thin film. The vacuum tube problem consumed the first 6 months of development. Standard radio tubes of the era measured several inches tall and contained electrode assemblies suspended inside glass envelopes by thin wire supports. Under normal use, these tubes were fragile. Under 20,000 Gs of acceleration, they would shatter instantly. Section T engineers started by literally dropping tubes off buildings to test survivability. They'd climb to the roof of the Carnegie Institution, drop vacuum tubes onto concrete, then examine the wreckage to understand failure modes. It was crude, but it generated data. Most tubes failed when their internal supports bent or broke, allowing the electrodes to short-circuit against the glass envelope. The solution came from an unexpected source: hearing aid manufacturers. In the late 1930s, companies like Raytheon and Western Electric had developed miniaturized vacuum tubes for portable hearing aids. These tubes were smaller than standard radio tubes and used different construction techniques. Instead of wire supports, the electrodes were mounted on more rigid structures. The glass envelopes were thicker, less prone to fracturing. Section T acquired samples of these hearing aid tubes and modified them further. They potted the tubes in wax, filling any air gaps inside the assembly to prevent mechanical vibration. They redesigned the electrode structures using planar arrangements, where components lay flat rather than extending vertically, reducing stress from centrifugal force. They thickened specific areas of the glass envelope where stress analysis predicted fractures would occur. By January 1942, they had vacuum tubes that could sometimes survive being fired from a gun. The first actual shell test occurred on January 29, 1942, at the Naval Proving Ground in Dahlgren, Virginia. Section T engineers loaded their prototype fuses into 5-inch shells and fired them from a standard 5-inch .38 gun at various elevations. The shells arced over the Potomac River and splashed down in the water. Navy divers recovered them, and engineers opened the shell noses to examine the fuses. 52% had survived launch. 52% had armed successfully. 52% had transmitted radio signals that could theoretically have detected targets. 52% was nowhere near the 80% reliability that Tuve had set as a minimum acceptable threshold. But it was 52% more successful than British photoelectric fuses had been. The Navy Bureau of Ordnance looked at those numbers and made a calculated decision. Start production now. Refine reliability as manufacturing continues, because waiting for perfection meant more ships sinking while engineers pursued marginal improvements. In February 1942, the Crosley Corporation in Cincinnati received a contract to begin pilot production of Mark 32 proximity fuzes. Crosley manufactured radios and household appliances. They knew electronics. They knew mass production. What they didn't know was how to build anything designed to be fired from a cannon. The learning curve was vertical. Crosley engineers had to design assembly lines where workers handled explosive components while maintaining electrical grounding to prevent static discharge detonation. They had to source vacuum tubes from Sylvania, who had to build entirely new production facilities staffed primarily by women workers. Men were being drafted who turned out 1 million miniature tubes every 2.5 days. By September 1942, Crosley was producing functional fuses. Reliability had climbed to 68%, still short of ideal, but combat viable. The Navy loaded 5,000 fuses into specially marked shells and prepared them for shipment to Pearl Harbor. Then came the moment that would define whether 18 months of desperate engineering work had produced a weapon or an expensive failure. August 12, 1942. USS Cleveland, a newly commissioned light cruiser conducting shakedown trials in Chesapeake Bay. The Navy had arranged a live-fire test using remote-controlled target drones, essentially modified aircraft flown by radio operators from the ground. Cleveland's gun crews loaded shells equipped with Mark 32 fuses into their 5-inch guns. The first target drone appeared, executing a simulated torpedo run at low altitude. Cleveland's forward battery tracked the target and opened fire. 10 rounds, the first proximity-fused shells ever fired in combat conditions, against a maneuvering aerial target. The drone disintegrated. Shrapnel from at least 2 shells passing within 70 feet had shredded its control surfaces and engine. It crashed into Chesapeake Bay within 30 seconds of Cleveland opening fire. The test team requested a second drone. Same result. 10 rounds fired, target destroyed. They requested a third drone. The range officer informed them no additional drones were available. Target drones normally survived hundreds or thousands of practice rounds before cumulative damage required their replacement. Losing 2 drones in one morning was unprecedented. Cleveland's commanding officer received orders to proceed immediately to the Pacific and not discuss the test with anyone. The Navy cancelled the remainder of the scheduled 2-day evaluation. They'd seen enough. Production orders went out that afternoon to Crosley, RCA, Eastman Kodak, General Electric, and McQuay Norris. Ramp up immediately. Build as many as physically possible. Cost per unit in September 1942, $732. That would drop to $18 by war's end through manufacturing optimization, but in autumn 1942, the Navy was paying the equivalent of $11,000 per fuse in today's currency. They didn't care. The mathematics were irrefutable. If proximity fuzes reduced ammunition expenditure per kill from 600 rounds to 100 rounds, that 6-fold improvement justified any cost. The first combat-ready fuzes shipped to Pearl Harbor in November 1942. Commander William Deke Parsons, a naval ordnance officer who'd worked closely with Section T and would later become famous for arming the atomic bomb aboard Enola Gay, personally escorted the shipment. 5,000 shells loaded with Mark 32 fuses, divided among 3 vessels judged most likely to engage enemy aircraft: USS Enterprise, USS Saratoga, and USS Helena. Personnel aboard all 3 ships received intensive training on proper handling procedures. The fuses were more sensitive than standard ordnance. They required different storage conditions. They couldn't be subjected to strong electromagnetic fields, which meant keeping them away from certain radar equipment. They had to be loaded into guns within specific time windows once armed. And absolutely critically, they could only be used over water. The potential consequences of a dud shell falling into Japanese hands were deemed catastrophic. If enemy engineers recovered an intact proximity fuse and reverse-engineered the technology, they could develop countermeasures or build their own versions. The strategic advantage would evaporate. So the orders were explicit. Use proximity fuses only in situations where shells would fall into the ocean if they missed. No firing over land, no firing near islands where duds might be recovered. Deep water only. This restriction would remain in place through most of 1943, limiting proximity fuse use primarily to naval engagements. But in those naval engagements, the technology would prove its worth beyond any projections. Helena's guns were among the first to demonstrate what the new fuses could do. Between October and December 1942, Helena participated in multiple night actions around Guadalcanal, using conventional time-fused ammunition because proximity fuses weren't yet available. Battle of Cape Esperance on October 11th. Naval Battle of Guadalcanal on November 13th. Her gun crews fired thousands of rounds, achieved respectable hit rates given the circumstances, but consumed ammunition at rates that logistics officers found deeply concerning. Then, in January 1943, Helena's magazines received their first shipment of proximity-fused ammunition, 500 rounds. The instructions were to mix them with conventional shells, some proximity-fused, some time-fused, to prevent gun crews from becoming over-reliant on the new technology if supplies ran short. On the morning of January 5th, when those 4 VALs appeared over Guadalcanal, Lieutenant Cochrane's battery fired 3 shells. At least one was proximity-fused. That single shell, detonating 70 feet from a target travelling at 200 miles per hour, accomplished what normally required hundreds of rounds of barrage fire. The gunners aboard Helena didn't fully understand what they'd done. They knew their shells had functioned differently. They'd been trained on the basics the fuses would detonate near targets automatically, but the actual mechanism remained classified above their clearance level. What they did understand was that they'd hit a target at range and deflection angles that should have been nearly impossible. Word spread through the Pacific Fleet with remarkable speed. Other ships began receiving proximity-fused ammunition through early 1943. Initial combat reports confirmed what Cleveland's test had suggested. Ammunition expenditure per kill dropped dramatically. By mid-1943, shells equipped with proximity fuses were accounting for over half of all aerial kills, despite representing only 25% of ammunition expended. The mathematics spoke for themselves. During 1943, Navy vessels in the Pacific fired 9,128 proximity-fused shells and shot down 61 aircraft. 155 rounds per kill. Compare that to 508 rounds per kill using time fuses during the same period, and the tactical advantage becomes overwhelming. But statistics only tell part of the story. The real transformation was psychological, both for American gun crews and Japanese pilots. American gunners gained confidence. They knew that if they could put shells anywhere near an incoming aircraft, the fuse would handle the final timing automatically. This reduced stress, improved crew performance, and created a positive feedback loop where better performance justified aggressive engagement at longer ranges. Japanese pilots faced the opposite effect. Their intelligence services couldn't determine why American anti-aircraft fire had suddenly become so much more lethal. Some pilots reported seeing no shell bursts, proximity-fused shells, detonated with less visible smoke than time fuses, making it impossible to judge where the defensive fire was concentrated. The psychological impact of invisible but deadly fire disrupted attack runs and forced Japanese commanders to assign more aircraft per strike, which meant fewer strikes overall. The technology's limitations, however, remained significant. Proximity fuses required targets moving through the radio beam at sufficient velocity to generate detectable Doppler shift. Against very slow-moving targets or targets approaching head-on with minimal angular velocity, the fuses might not trigger reliably. They also couldn't distinguish between aircraft and large pieces of debris, leading to occasional premature detonations when shells passed too close to burning wreckage. Manufacturing quality varied. Even as production ramped up through 1943, fuse reliability fluctuated between 60 and 75%. 1 in 4 shells might fail to properly arm, fail to transmit, or fail to detect targets. This meant gun crews still needed to fire multiple rounds per target, but 4 rounds with a 25% failure rate still dramatically outperformed 600 rounds of barrage fire. The Fletcher-class destroyers, entering service throughout 1942 and 43, became ideal platforms for proximity-fused ammunition. With 5 5-inch guns capable of collective fire rates exceeding 100 rounds per minute and sophisticated Mark 37 fire control directors, Fletchers could pour proximity-fused shells into engagement zones at rates that made enemy air attacks suicidal. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The proximity fuses true test came in 1945, when the strategic calculus of the Pacific War shifted from conventional air combat to something far more terrifying: organized suicide attacks. The Japanese High Command, recognizing they were losing the war of attrition, made a calculated decision in October 1944. Conventional bombing required skilled pilots who took years to train. Japan no longer had years. They no longer had fuel for extensive training. What they did have were thousands of young men willing to die for the emperor and aircraft that could be flown on one-way missions. The kamikaze program transformed the tactical equation. A conventional bomber pilot wanted to survive. He would break off attacks if defensive fire became too intense. He would take evasive action. He would retreat if his aircraft took damage. A kamikaze pilot had no such concerns. Once he entered his dive, nothing short of complete destruction would stop him. Wounding his aircraft didn't matter. Killing him didn't matter unless it happened before he reached his target. This created a horrifying challenge for American gunners. Time-fused shells were nearly useless against kamikazes. The problem was closure rate. A kamikaze diving at 400 miles per hour closed the distance between detection and impact so rapidly that fire control computers couldn't keep pace. By the time a shell with a time fuse reached where the computer predicted the target would be, the kamikaze had already passed through that airspace and was 2,000 feet closer to its target. Proximity fuses changed this completely. The shell didn't need to predict anything. It simply needed to get close. The fuse would handle detonation timing automatically, creating a lethal burst zone that the kamikaze had to pass through. Even if the pilot was already dead, already unconscious, already committed to his final dive. If his aircraft passed within 70 feet of a proximity-fused shell, it would be shredded. Okinawa became the crucible where this technology faced its ultimate test. The invasion began on April 1, 1945. For the next 3 months, Japanese forces launched over 1,500 kamikaze sorties against the American fleet anchored off the island's coast. The statistics were apocalyptic. The Navy lost 21 ships sunk outright, and 66 damaged severely enough that many were still under repair when the war ended. But those numbers, horrific as they were, represented a defensive success when measured against Japanese attack intensity. Consider what happened on May 11, 1945, during a kamikaze raid that has since become legendary in naval gunnery circles. 2 Fletcher-class destroyers, USS Hugh Hadley and USS Evans, were stationed on radar picket duty northwest of Okinawa. Radar picket stations were essentially sacrificial positions. Destroyers would position themselves 50 to 80 miles from the main fleet, serving as early warning systems for incoming air attacks. The Japanese knew exactly where these picket stations were located, and they targeted them mercilessly. On the morning of May 11th, radar operators aboard Hadley detected massive inbound formations. The count eventually reached 156 aircraft. Most were kamikazes. The 2 destroyers, along with 4 small landing craft serving as support vessels, faced an attack larger than most task forces had encountered during the entire war. What followed was 90 minutes of sustained combat that tested every limit of naval anti-aircraft doctrine. Hadley and Evans both carried the full Fletcher-class armament, 5 5-inch dual-purpose guns, multiple 40mm Bofors mounts, and 20mm Oerlikon cannons for close-range defense. Their magazines were loaded with a mix of proximity-fused and conventional ammunition. The after-action reports documented by the Bureau of Naval Personnel tell a story almost beyond belief. Hadley's 5-inch batteries maintained fire at near maximum rate for the entire engagement. Her gun crews cycled through the loading sequence shell from magazine to hoist to fuse setter to gun with mechanical precision, even as kamikazes crashed into the sea around them. The proximity fuzes performed exactly as designed. Shells detonating 70 to 100 feet from incoming aircraft created overlapping kill zones. Japanese pilots diving at terminal velocity had perhaps 2 seconds between entering the engagement envelope and either hitting their target or crashing. In those 2 seconds, Hadley's guns put proximity-fused shells into airspace that the kamikazes had to transit. Hadley shot down 12 confirmed kills. Evans accounted for 23 before taking 4 direct hits from aircraft that were already burning from anti-aircraft fire, but maintained sufficient momentum to reach their target. The 2 destroyers and their support craft, representing less than 3,000 tons of combined displacement, faced an attack that would have overwhelmed a cruiser division in 1942. The verdict from fleet commanders: indispensable. That was the official assessment of proximity fuses' performance during Okinawa. Not helpful. Not advantageous. Indispensable. Without them, the losses at Okinawa would have exceeded anything the Navy could sustain, but the campaign cost was still staggering. Of the 25 Fletcher-class destroyers lost or written off as constructive total losses during World War II, 17 went down between March and July 1945 off Okinawa. Not because proximity fuses didn't work, because the Japanese were throwing aircraft at the fleet faster than any defensive system could shoot them all down. Some naval historians have argued that Japan's decision to implement mass kamikaze attacks was partially motivated by the devastating effectiveness of American anti-aircraft fire against conventional bombing runs. Skilled pilots who'd survived the 1942 and 43 campaigns were being shot down at unsustainable rates. Training new pilots to the same skill level would take years Japan didn't have. But flying an aircraft into a ship required minimal training, a few hours learning basic controls, basic navigation, enough to get the aircraft to the target area. After that, gravity and commitment did the rest. It was a strategic calculation born of desperation, and proximity fuses made it more costly than it would have been. But they couldn't stop it entirely. The mathematics were too brutal. With 156 aircraft attacking 2 destroyers, even 90% kill rates far higher than any defensive system had ever achieved meant 15 aircraft getting through. And it only took 1 kamikaze strike to mission kill a destroyer. The Pacific Theater statistics for proximity fuses through the end of the war tell the story of a weapon that transformed aerial combat but couldn't single-handedly prevent losses. During 1945, Navy vessels fired approximately 421 proximity-fused shells per confirmed kill. That number seems worse than the 155 rounds per kill from 1943, but context matters. The 1945 targets were kamikazes attacking at maximum speed with no evasive maneuvering and no concern for survival. The engagement times were shorter, the closure rates were faster, and American doctrine had shifted to opening fire earlier and maintaining fire longer, which increased ammunition expenditure but also increased the number of targets engaged. Analysis conducted after the war by Ralph Belknap Baldwin, one of the proximity fuses developers at Johns Hopkins Applied Physics Laboratory, examined 278 confirmed kills between October 1944 and August 1945. His team calculated that only 46 of those aircraft would have been destroyed using time-fused ammunition. The proximity fuse increased kill probability by approximately 600%. That 6-fold improvement saved thousands of American lives. It also revealed something unexpected. The proximity fuse's most important contribution might not have been the aircraft it destroyed, but the attacks it prevented. Japanese commanders, observing the casualty rates their aircrews suffered, were forced to assign more aircraft per strike to achieve the same probability of successful target engagement. This meant fewer total strikes, which meant American ships spent less time under attack, which reduced crew fatigue and improved overall fleet effectiveness. While the Navy fought kamikazes in the Pacific, the proximity fuse was transforming ground warfare in Europe through an application that engineers had considered theoretical until late 1944. The restriction against using proximity fuses over land remained in effect through most of the European campaign. The risk of German forces recovering an intact fuse was deemed too high, but in December 1944, circumstances changed dramatically. December 16th, German forces launched a massive surprise offensive through the Ardennes forest. The Battle of the Bulge. American lines buckled under the assault. Weather conditions grounded Allied aircraft, eliminating air superiority that American ground forces had relied on since D-Day. German panzer divisions pushed deep into American positions, creating a salient, the Bulge, that threatened to split Allied forces. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, faced a crisis. His ground forces needed artillery support to stop the German advance, but weather prevented air support, and visibility was so poor that standard artillery had limited effectiveness. Then someone remembered the proximity fuses. The army had received fuses modified for use in 105mm and 155mm howitzer shells. These were supposed to be held in reserve for the invasion of Japan, but Japan was 6 months away, and the Bulge was happening now. Eisenhower authorized their use, calculating that even if Germans captured intact fuzes, the war would be over before they could reverse engineer and deploy countermeasures. The effect was immediate and devastating. When properly employed, proximity-fused artillery shells detonated 15 to 30 feet above the ground, creating an airburst that scattered shrapnel in a cone-shaped pattern across a wide area. This was far more lethal than conventional shells that detonated on impact, which buried most of their explosive force in the ground and created shrapnel patterns that were easily defeated by foxholes and trenches. General George Patton, commanding the Third Army, wrote to the War Department describing the shells as devastating. He recounted one engagement where his artillery caught a German battalion attempting to cross the Sauer River. A single battalion-level concentration of proximity-fused shells killed 702 enemy soldiers by actual count. 702. In one artillery barrage, Patton concluded his letter with a prediction. "I think that when all armies get this shell, we will have to devise some new method of warfare." He was correct. Proximity-fused artillery made conventional infantry tactics obsolete overnight. Troops couldn't hide in trenches. They couldn't use natural terrain features for protection. They couldn't rely on being below the burst height of conventional artillery. The shells detonated above them regardless of cover, and the shrapnel came down in a lethal rain that penetrated foxholes and slit trenches. German prisoners interrogated after the battle reported that these airburst attacks created more psychological trauma than any other weapon they'd encountered. There was no defense. Conventional artillery could be mitigated through proper use of terrain and entrenchment. These new shells seemed to ignore all defensive doctrine. One prisoner described them as quick, powerful bursts, for which there was simply no defense. The technology's impact extended beyond immediate tactical advantage. German forces captured approximately 20,000 proximity fuzes when they overran an American ammunition depot during the early days of the Bulge. German engineers examined them, recognized what they were looking at, and immediately began reverse engineering efforts. But German scientists concluded the devices were impossible. They calculated the acceleration forces involved in artillery fire and determined that vacuum tubes could not survive those conditions. Therefore, what they were examining must be some form of elaborate decoy or propaganda. They filed reports stating that the Americans were using conventional impact fuses and that the supposed proximity fuses were Allied psychological warfare. This might rank among the most consequential intelligence failures of the war. German engineers, unable to believe that vacuum tube technology could be hardened sufficiently, rejected the evidence of their own examination. They had working examples. They had the circuit diagrams visible through dissection. They had everything needed to understand the technology, and they concluded it was fake because their theoretical calculations said it couldn't work. Meanwhile, American production of proximity fuses hit 70,000 units per day by war's end. Over 22 million fuses were manufactured between 1942 and 1945 at a total program cost of approximately $1 billion, $15 billion in modern currency. 87 different companies using 110 factories contributed to production. Sylvania alone employed 10,000 workers, 95% of them women, producing miniature vacuum tubes at rates that exceeded 2/3 of the entire pre-war American radio industry's output. The fuse's final major combat use came in July 1945 during carrier raids against Japanese naval bases. Approximately 1/3 of all bombs dropped during these raids carried proximity fuses modified for use in unrotated projectiles bombs rather than artillery shells. The fuses were configured to detonate at specific altitudes above anti-aircraft gun positions, saturating those positions with shrapnel and silencing them before the main bomber formations arrived. The effectiveness was so pronounced that Japanese anti-aircraft defense effectively collapsed during the final weeks of the war. Gun crews who survived the initial proximity-fused suppression attacks abandoned their positions rather than face subsequent raids. The psychological impact of weapons that seemed to anticipate and counter every defensive measure contributed to Japan's deteriorating military position in the weeks before Hiroshima and Nagasaki. When the war ended in August 1945, proximity fuse technology represented one of the three most significant technical developments of the conflict, alongside radar and the atomic bomb. Secretary of the Navy James Forrestal stated it helped blaze the trail to Japan. Vannevar Bush, head of the Office of Scientific Research and Development, credited proximity fuses with three critical effects: defense against kamikazes in the Pacific, defense against Vone flying bombs over England, and increased effectiveness of field artillery in Europe. But the technology's true significance wasn't just what it accomplished during World War II. It was what it revealed about the fundamental nature of modern warfare. For centuries, artillery had operated on a simple principle: point the weapon at the target, fire the projectile, hope it arrives at the right place at the right time. This required increasingly sophisticated predictions, ballistics calculations, wind adjustments, target motion estimation, but it remained fundamentally reactive. The gunner had to predict. The fuse had to be set in advance. Once the shell left the gun, its behavior was predetermined. Proximity fuses inverted this relationship. The shell became an active participant in its own terminal guidance. It sensed the environment. It made decisions. It adjusted its behavior based on real-time information that didn't exist when it was fired. This was the first true smart weapon. The conceptual leap from dumb projectile to sensing projectile enabled everything that followed. Modern guided missiles use the same principle scaled up enormously. An AIM-120 AMRAAM air-to-air missile doesn't just fly toward where the target is predicted to be. It actively tracks the target, adjusts its trajectory continuously, and makes terminal corrections based on real-time sensor data. That's a proximity fuse with wings and propulsion. Ship-based defensive systems like the Phalanx close-in weapon system fire thousands of rounds per minute at incoming missiles, with each round carrying proximity fuses that optimize fragmentation patterns. Modern artillery shells can be programmed mid-flight to adjust their airburst height based on changing tactical conditions. Smart mines detect approaching vehicles and detonate at optimal standoff distances. All of these systems descend directly from the work that Section T accomplished between 1940 and 1942, putting sensors and decision-making capability into the munition itself. The Fletcher-class destroyers that carried proximity-fused ammunition into combat at Guadalcanal, Okinawa, and dozens of other engagements throughout the Pacific represented the first generation of naval vessels where defensive systems could genuinely protect against aerial attack. Previous destroyers could harass aircraft, could force them to maneuver, could occasionally shoot one down through volume of fire or extraordinary luck. Fletchers equipped with proximity fuzzes could reliably destroy aircraft at ranges exceeding 6 miles. That 6-mile engagement enveloped the effective range at which 5-inch guns firing proximity-fused shells could achieve reliable kills changed naval tactics fundamentally. It meant carrier groups could position destroyers as pickets far enough from the main formation to intercept attacks before they reached high-value targets. It meant amphibious assault forces could operate with destroyer escorts that provided genuine air defense rather than psychological deterrence. The technology also drove doctrinal changes in how navies approached air defense. Pre-war doctrine assumed that some percentage of attacking aircraft would always penetrate defenses. The goal was minimizing that percentage through positioning, fighter coverage, and volume of fire. Post-proximity fuse doctrine assumed that properly configured defensive systems could achieve near-total intercept rates against conventional attacks. The goal shifted from damage mitigation to attack prevention. This created a strategic feedback loop. As American air defenses became more lethal, Japanese forces were compelled to adopt tactics kamikazes that had higher probability of penetrating those defenses. This forced further improvements in defensive systems, which drove further desperation in offensive tactics. The cycle continued until one side collapsed from accumulated losses. Some military historians argue that Japan's decision to implement mass kamikaze attacks represented a recognition that conventional tactics against proximity foes' defenses were unsustainable. Training a pilot to the skill level where he could successfully conduct a bombing run, evade defensive fire, and return to base took 18 months. Training a kamikaze pilot took 3 weeks. The mathematics of that exchange ratio, combined with American defensive capabilities, left Japan with limited options. Whether proximity fuzes directly caused the kamikaze program or simply accelerated its implementation remains debated. What's undeniable is that the fuzes made every other Japanese tactical option statistically untenable. The human cost of developing this technology deserves acknowledgement. Section T's research facilities, scattered across Maryland and Virginia, operated under wartime pressure that demanded results faster than safety protocols would normally permit. Test firings occasionally resulted in premature detonations that killed or injured researchers. Manufacturing facilities faced similar hazards. Crosley Corporation's proximity fuse assembly lines required workers to handle components that could detonate if mishandled or if static electricity built up during dry weather. 2 fatal accidents occurred in 1944 at the 3 main proximity fuse manufacturing plants. Both involved transportation of assembled fuses rather than production line failures, but they highlighted the inherent risks of manufacturing weapons at scales measured in millions of units. That only 2 fatal accidents occurred across 3 years of production, involving hundreds of thousands of workers handling millions of explosively armed devices, represents extraordinary attention to safety protocols developed specifically for this program. The workers who built proximity fuses, predominantly women, as most men of working age were in military service, received training, emphasizing meticulous attention to detail and strict adherence to grounding procedures. They wore cotton clothing to minimize static buildup. They worked on conductive floor mats connected to building ground systems. They handled components with procedures that would seem excessive for any other manufacturing environment, but were absolutely necessary when every unit contained explosives and electrical systems that could trigger detonation. These workers likely never fully understood the strategic importance of what they were building. Security protocols prevented detailed disclosure of how the fuses functioned or where they were being used. But they understood that the shells they assembled were going to American servicemen fighting overseas, and that the quality of their work directly impacted whether those servicemen survived. Betty Fitzgerald, who worked at Crosley's Cincinnati facility from November 1943 through war's end, described the atmosphere in a 1986 oral history interview. "We knew lives depended on our work. Every shell we assembled, we thought about some sailor or soldier who'd be using it. You didn't cut corners. You didn't rush. You treated every component like it mattered. Because it did." The post-war disposition of proximity fuse technology followed predictable patterns. The United States maintained classification restrictions through the late 1940s, though the basic principles had been disclosed in September 1945 when military censorship relaxed. Soviet espionage acquired working models through multiple channels, including Julius Rosenberg, who stole proximity fuse designs while working for a defense contractor in the mid-1940s. By the Korean War, Proximity fuses had become standard equipment across all American artillery and naval systems. The improved Mark 18 fuse, introduced in 1947, offered better reliability and could be manufactured at lower cost. When Fletcher-class destroyers returned to combat during Korea, their 5-inch batteries fired proximity-fused ammunition almost exclusively, achieving ammunition-to-kill ratios that would have seemed impossible in 1942. The technology continued evolving through subsequent decades. Solid-state electronics replaced vacuum tubes in the 1960s, enabling miniaturization that allowed proximity fuses in much smaller calibers. 40mm shells, previously too small to accommodate the necessary electronics, gained proximity fuse capability. Modern versions use microprocessors and can be programmed mid-flight to adjust detonation parameters based on target type. Contemporary naval vessels like the Arleigh Burke-class destroyers carry 5-inch guns that fire proximity-fused ammunition, fundamentally similar in concept to what Helena used in January 1943. The fuses are more sophisticated. They can distinguish between aircraft, missiles, and debris. They can adjust fragmentation patterns based on target aspect angle. They can operate in electronic countermeasure environments that would have jammed World War II-era fuses. But the core principle remains unchanged. Detect the target, detonate at optimal range, maximize probability of kill. The philosophical implications of proximity fuses extend beyond military applications. They represented one of the first practical implementations of closed-loop control systems in high-stress environments. Engineers working on Section T developed techniques for building electronics that could survive extreme acceleration, extreme temperatures, and hostile environments while maintaining reliable operation. These techniques informed post-war development of electronics for missiles, spacecraft, and industrial systems operating in harsh conditions. James Van Allen, who contributed to vacuum tube development for proximity fuses while at Johns Hopkins Applied Physics Laboratory, later designed scientific instruments for America's first successful satellite, Explorer 1, launched in 1958. The instruments had to meet similar requirements: small size, extreme ruggedness, reliable operation in space's harsh environment. Van Allen drew directly on knowledge gained from designing proximity fuse electronics. The feedback loop between military research and civilian technology that characterized the Manhattan Project and radar development applied equally to proximity fuzzes. Manufacturing techniques developed for mass-producing miniature vacuum tubes accelerated post-war consumer electronics development. Assembly line practices refined while building millions of fuses informed television and radio manufacturing in the 1950s. Even the concept of building complex electronics that could survive rough handling critical for proximity fuses influenced consumer product design philosophy. But the most significant legacy might be conceptual rather than technological. Proximity fuses demonstrated that weapons could be made intelligent enough to make terminal guidance decisions autonomously. This opened questions that military planners and ethicists are still grappling with 80 years later. If a shell can decide when to detonate, what other decisions can weapons make? Should they? At what point does autonomous decision-making become problematic? Modern debates about autonomous weapon systems, artificial intelligence in military applications, and the ethics of removing human oversight from lethal force decisions all trace intellectual lineage back to proximity fuses. They were the first weapons that sensed their environment and took action without human input after being deployed. That threshold, once crossed in 1943, established precedent for every subsequent development in autonomous weapons. The men who served aboard Fletcher-class destroyers in the Pacific operating 5-inch guns that fired proximity-fused shells at kamikazes, diving toward their ships at 400 miles per hour, didn't think about philosophical implications. They thought about survival. They thought about protecting their shipmates. They thought about shooting down the next incoming aircraft before it could hit. But their experiences demonstrated something profound about technological warfare. The side that can build weapons responding, Faster than human reaction times gains decisive advantage. Proximity fuses responded in microseconds. Human gunners required seconds to process visual information and make decisions. That difference, measured in thousandths of seconds, determined whether ships sank or survived. Every advancement in military technology since has pursued the same goal: compress decision cycles to timescales shorter than the enemy can react. Radar-guided missiles, computer-controlled point defense systems, network-centric warfare doctrine, all attempt to move inside the enemy's decision loop, making it impossible for them to react before the engagement concludes. Proximity fuzes pioneered this approach, and they did it with vacuum tubes, mechanical batteries activated by centrifugal force, and analog amplifier circuits that would be considered laughably primitive today. Yet they increased anti-aircraft effectiveness by 600%. They changed tactics across multiple theaters of war. They influenced strategic decisions about attack profiles and defensive postures. And they started with one simple observation: hitting a moving target is hard, but detecting when you're near a moving target is much easier. Let the shell handle the detection problem, and suddenly the impossible becomes routine. She was sunk by Japanese destroyers during the Battle of Kula Gulf on July 6, 1943, 6 months after achieving the first proximity fuse kill. 3 Type 93 torpedoes struck her port side, breaking her keel and sending her to the bottom in less than 20 minutes. 168 of her crew died. The remainder were rescued by destroyers or reached shore and were evacuated later. Helena's wreckage was located in April 2018 by Paul Allen's research vessel Petrel, resting in over 3,000 feet of water north of the New Georgia Islands. She's a war grave, protected under international law, resting in the same waters, where she demonstrated technology that would help win the war. The Fletcher-class destroyers that continued fighting through 1945, firing proximity-fused shells at kamikazes off Okinawa, represented the operational vindication of everything Section T had attempted. Those destroyers, each carrying approximately 400 rounds of 5-inch ammunition, could engage aerial targets with confidence that their shells would detonate near threats even if direct hits weren't achieved. This transformed the defensive calculus entirely. Previous generation destroyers hoped to survive air attacks. Fletcher-class destroyers, equipped with proximity fuses, expected to defeat air attacks. That psychological shift from survival to victory as the baseline expectation reflected the magnitude of what proximity fuses accomplished. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.